All right, here is my budget DIY air conditioner. I'm gonna walk you all through some of the basics on how it works, and then we'll turn it on, and then I will also go into some theoretical predictions and how we analyze these systems. But first, let's talk about how this works. So here we have our submersible pump, which is going to pump our water, which is supposed to be in an ice bath. The ice melted rather quickly, and so I got an ice pack from the faculty lounge, and that's what we're going to go with. So we're going to pretend this is all at 0 degrees Celsius, and we go up through this pipe, and then we go into our main air conditioner area. So copper has been selected because it has a really high thermal conductivity as well as electrical conductivity. So as the cold water circulates through all of these coils, it's in contact with the surrounding air environment, and so heat will leave from the air through the pipes into the water, which will, as it continues to circle out through here, and then come back out through this end of the pipe and back into the ice bath where it would cool back down to around freezing. And the cycle continues as we continue pumping more water through, and heat continues to leave the surrounding areas. So let's turn it on and see it in action. So. And there we go. Now, some of the parameters that determine how well or not well our air conditioner is able to conduct heat from the environment include the diameter of the pipe. So we can also manipulate the length of coils. So with more coils, we have more surface area in contact with the environment, and so that would also increase our overall heat transfer. And then finally, we can also increase our pumping power. So here is kind of a medium-sized submersible pump. However, if our pump was stronger, we would get, again, an increased mass flow rate through the coils, and so that would also lead to an overall increased rate of heat transfer. So I'm gonna now go into some theoretical backing for the things I just said, as well as some other reasons why we chose some of the factors that are in this pipe, and then how we can calculate all these things, including our convection coefficients, which determine how quickly heat transfers from the air to the outside surface of the pipe, then conduction from the thin pipe to the water, and then internal convection inside the fluid that is traveling through the pipes is our total heat transfer. So I'm going to go through the theoretical predictions for that and how we can calculate those things and analyze our overall performance of this air conditioner.
All right, and we are back. So now we will do some calculations on some experimental data collected from our DIY air conditioner setup. So we are going to find the internal and external convective coefficients to be able to find the heat transfer rate and the overall coefficient of performance of our setup. Also, these experimental values include a fan present as well. So a fan will help promote airflow over the surface of our copper tubes, which would increase our overall overall air conditioning performance. However, that was not included in the set that I showed you because with the fan on and the pump going, it was just really hard to hear my voice as I was recording. But in the real setup, there is also a fan present. So the values that we have here are the inner and outer diameters of our pipe, the overall pipe length, the fill volume and time needed to fill that volume, which we'll use to find our volumetric flow rate, the water inlet mean temperature, the water outlet mean temperature, so the average temperatures of the water entering and exiting, respectively, the pipe, the tube outer surface temperature, so the surface temperature of the pipe, of the outside of the pipe, the ambient air temperature, the fan input power, and also the pump input power. So we use all these values, and then first up we'll find the Reynolds number, and then we will find the internal convection coefficient, the external convection coefficient, and then we will find the heat transfer rate, so how much heat our air conditioner is pulling from the outside, and the coefficient of performance. So first, to find the Reynolds number, I find the volumetric flow rate from that volume and that delta T, and I convert it into meters cubed per second. And I also find the mass flow rate by multiplying my density by that volumetric flow rate. I'm not going to use this immediately, but it will come in handy later. Using my volumetric flow rate and the cross-sectional area of my pipe, I'm able to find my mean velocity. And I use the cross-sectional area of my pipe because this is the quantity that I care about, this arrow going through the pipe. And so if I only want to isolate this section of my total volumetric flow rate, or kind of like my volumetric velocity, I want to divide that by my cross-sectional area here. And once I know my mean velocity, I can then find my Reynolds number, which is my density times my mean velocity times my diameter of the inside of the pipe, so the actual area of the pipe that the water is flowing through. And then all of that divided by my dynamic viscosity of the water, evaluated at 0 degrees Celsius. Since my water is entering in from an ice bath, I'm evaluating all of my temperature-dependent fluid properties at 0 degrees Celsius, and I'm also at atmospheric pressure. So that comes out to be about 8,000, which is greater than 2,300. So it flows with a Reynolds number less than 2,300. We call those laminar flows, but greater than 2,300, those tend to be turbulent flows. And that will be good to know because that will help me determine some of the different equations I will use later on. So the next thing I find is my average internal convection coefficient. This is an average because this is going to change to the pipe, especially because we're in turbulent flow. So the water is going to be flowing differently and kind of in unexpected and unpredictable ways. We're in kind of like a chaotic mode. However, we can find kind of an average internal convection coefficient through the water, and that will help us kind of approximate it for the whole system. And I can find that using this equation here. Which is my thermal conductivity of my water, denoted here K sub W, times my diameter of the inside of the pipe, and multiplied by this Nusselt number, which is kind of similar to the Reynolds number, and then it's also a dimension in this quantity, but the Nusselt number is the ratio of convective to conductive heat transfer at a boundary in a fluid. And then I can use a different kind of correlation, which here is an empirical correlation between the Nusselt number and the Reynolds number and the Prandtl number. The Nusselt number is a hard thing to directly measure, and so this is why we switch it over using this correlation between those. Because I can find my Reynolds number pretty easily, and my Prandtl number is yet another dimensionless quantity that relates to the thermal diffusivity and the momentum diffusivity of a fluid. Diffusivity, there we go. So then after plugging in all those values and the thermal conductivity of water, again at 0 degrees Celsius, we arrive at this value for my convective coefficient of the inside, so again through the water, which is it's like 2,500 watts per meter squared times Kelvin. So then continue on. I want to now find my external convection coefficient, h bar on the outside. So this is my convection coefficient through the air. So how good is my air at transferring heat? And I can do this by first setting up this network of thermal resistors. So here's kind of a diagram of the overall heat transfer, which is entering from the environment in through the thickness of the pipe here, which is kind of hard to see, it's pretty small. And then the heat then enters the water flowing through the pipe. And so I can set up like a series of resistors. You can think about the heat like a current, and then each of those steps like different resistors. So here is first my resistance from the convection from the outside, which is just 1 over my convection coefficient multiplied by my surface area now. Not my cross-sectional area, my surface area. So I want to know how much pipe surface is in contact with the air. And then plus my my conductive resistance of my pipe. So how good, again, my pipe is at conducting heat through itself. And then finally, plus my convection resistance of the inside. And I can add all those together to get my total thermal conductivity resistance. And now we have a lot of equations, which I'm not going to explain too much about. But this is saying that my T infinity, which is just my ambient air temperature, minus my mean outlet temperature, divided by my, again, T infinity, my mean air temperature, minus my TMI, my mean inlet temperature, is equal to the exponential of the 1 over my total thermal resistance divided by my mass flow rate times my heat capacity. This gets pretty hairy with some math, but it's kind of intuitive in the sense that we would think that as my thermal resistance is lower, my outlet mean temperature is going to get warmer because that means I have less resistance, and so more heat would be pulled from the environment. So we run all this through to be able to find and isolate my average external convective coefficient, and we arrive at this value. Finally, we can find Q, which now looks strangely simple after all that effort. But I needed to find my external and internal convective coefficients to be able to find this actual value of my total thermal resistance. I can run that through, and I arrive at about 53 watts. So finally, to find my coefficient of performance of my DIY air conditioner setup, I can just take those 53 watts and divide it by my total power needed, which is to run my fan, my P sub F, and also run my pump, P sub P, and it's about 0.5. So this is kind of an engineering and application example of some of the things that we talked about in our class, and I hope you enjoyed.